What's up, guys? Welcome back. Patrick here. Moving on to the next example. We got to find the limit as x approaches 0 from the negative side of cosecant x minus 1 over x. So notice we can't do a direct substitution with 0 because this here is going to be undefined, 1 divided by 0. Also, this would be undefined because cosecant x, what's that equal to? That's equal to 1 over sine x. And then if we plug in 0 here, sine is 0, 0, 1 divided by 0 is undefined. So let's get into a little bit more detail to see what is happening as we approach 0 from the negative side. So values like, for example, negative 0.0001, right? A very small negative number that's getting closer and closer to 0. So let's start with cosecant x. So we know it's 1 over sine x. Now sine x, we know that that function looks like this, and then on the other side kind of looks like that, right? Keeps going on forever. So what's happening as we approach 0 from the negative side? Well, notice that the y values are approaching 0, but they're approaching 0 from the bottom. And so what's going to happen is you're going to end up having 1 divided by a very small negative number, right? Because as x approaches 0 from the negative side, then sine x is approaching 0 as well. The y values are approaching 0, but they're approaching 0 from the bottom. So it's going to be a very small negative number. Now, if we were approaching 0 from the positive side, then we'd be approaching this y value of 0 from above. And so we'd have very small y values. Okay, so this here, 1 divided by a very small negative number, this here is going to go towards negative infinity. Minus 1 over x. Now, 1 over x, if we graph that, it looks like this. So as we approach 0 from the negative side, this is 0 here. As we're approaching it from the negative side, notice that the function 1 over x is going towards negative infinity. So what we're going to end up having is negative infinity minus negative infinity. And that there is an indeterminate difference. If you remember, indeterminate differences can be one of two forms, either positive infinity minus positive infinity, or negative infinity minus negative infinity. All right, so unfortunately, because it's an indeterminate difference, we're going to have to figure out a different strategy to see what this limit is going to. And the way we can do that is we can actually take, you know what, I'll continue it over here. We could take that cosecant x and we could change it to 1 over sine x minus 1 over x. And let's combine these into one expression. So we would get a common denominator. Now the common denominator between these would be just both of these expressions multiplied together. So we'd have x sine x. And then at the top, we would end up with x minus sine x like that, right? We're taking this sine x, multiplying it by x, so we multiply the top by x. Taking this x, multiplying it by sine x, so we multiply the top by sine x. Right? So this expression is the exact same thing as this expression. And what's nice now is if we do a direct substitution of 0 here, we'd end up with 0 minus sine of 0, which is just 0. So 0 minus 0 is 0. And then 0 times 0 is just 0 as well. And so notice that now this, we change to this, and it's now an indeterminate quotient. Right? So we took an indeterminate difference and we converted it to be an indeterminate quotient. And so now because it's in this format, what we can try to do to solve this limit is apply L'Hopital's rule, right? So if we apply L'Hopital's rule, what's going to happen is we would take the derivative of the numerator, which would be 1 minus cos x. And then over here, we're going to have to apply the product rule because we got x times sine x. So the derivative of x is 1 times sine x is just sine x. And then the derivative of sine x is cos x. So we'd have plus x cos x, like that. So now let's see if we could do a direct substitution. If we plug in 0 for x, notice cos of 0 is 1. 1 minus 1 is 0. And then the denominator, sine of 0 would still be 0. And then this 0, this x would be 0. And then cos of 0 is 1. So 0 times 1 is 0. 0 plus 0 is 0. So it's still in this indeterminate form. It's still an indeterminate quotient. But let's try to apply L'Hopital's rule again, a second time. So if we do that, we would have the limit as x approaches 0 from the negative side. Now the derivative of 1 is 0. The derivative of cos x is negative sine x. With this negative here, turns into a positive sine x. All over, the derivative of sine x is cos x. And then here, x times cos x, we'd have to apply the product rule on that. So we'd end up with the derivative of x is just 1, so we'd have cos x, plus the derivative of cos x is negative sine x times x. So this would be minus x sine x. Now what happens when we do a direct substitution is sine of 0 would be 0. But notice now that the denominator won't be 0 because we'd have cos of 0 plus cos of 0, which would be 1 plus 1, minus 0 times 0. This whole thing would be 0, but we'd have 1 plus 1, which is 2. And then 0 divided by 2 is just 0. All right, so the answer to this limit is that it is 0. So just as a review, we took an indeterminate difference, converted it to a format where it was an indeterminate quotient, applied L'Hopital's rule twice, and then did a direct substitution. Final answer is 0.